Good afternoon, this is Professor Bridget Benson here to give you a tutorial on how to use iSIM to help you debug your CPU. So right in here I have Xilinx ISE up on my screen, and as you can see my top level file is the rat wrapper file that's highlighted here on the left, and beneath that I have the component of the CPU, which I have port mapped all of my CPU components, and therefore all the other files, all the components that are in the CPU are then listed right below here. The program counter, the scratch pad, register file, ALU, control unit, all the flag registers, etc. Alright, so I want to run my first program on this RAT CPU. So I'm going to go to the RAT simulator. And here you can see I've written the first program that we're going to try to run on this RAT CPU. And basically what this program is going to do is it's going to take the input from the switches. Here, let me assemble this here and step through it. It's going to take the input from the switches, which here I'll say we have 40 on the switches. It moves that value into the register R10, as you can see highlighted in the register column. Then it's going to move the value FF into R11. It will exclusive OR the values in R10 and R11, which basically toggles the input value on the switches, and then outputs that value, the toggled value of the switches, onto the LED port. So if the switch was on, the LED is off, and if the LED or if the switch is off, the LED is on. And it just stays in an infinite loop doing that over and over again. Okay, so we have assembled our program, therefore we can now use the generated program and put it into our Xilinx project. So if I go back to Xilinx, as you can see right now I don't have a program in here, so I'm going to right click and say add source, and I'm going to navigate to the folder where I just generated the program. And it's useful to look at the timestamp. If you look here at the date modified, I have this program 322 at 12:48. Then if you look down at the bottom of your screen, it is now 12:50. That one was probably the last one I did generate. So I got the right program that I want. I'll add that to my Xilinx project. Alright, and also I wanted to verify that in the RAT wrapper, if you look at the input port IDs for the switches and the output port IDs for the LEDs, notice the switch's ID is 20 and the LED's ID is 40. This has to match identically with the port IDs specified in the assembly program. So my switch port is 20 or hex 20 and my LED port is hex 40. So we are good there. If those do not match, make sure they do. Alright, so now we're ready to test this thing out. What I'm going to do now is add a test bench. So we can generate our own test bench. We're going to make a new source, and we'll click VHDL test bench. I'll call it RAT-TB for test bench, and we're going to add that to our top level, the RAT wrapper. And great, now we have generated a test bench. And we can give it some input stimulus. What I'm going to do is, in this stimulus process, I'm going to add this code here. So basically, in this test bench, we have to give input conditions, so therefore we can test to see if the code gives us the output we expected. So the only input we have to worry about here is, you can look here in the entity declaration, we have the switches, the reset, and the clock. Well, the test bench file has already generated a clock for us. We don't need to reset the signal, so we're going to give the switches some value. So in this stimulus process, we're going to wait for 100 nanoseconds, which is the equivalent of 10 clock cycles, and every 100 nanoseconds we're just going to add 1 to the switches. And we'll be expecting different results as a result of that. So I'm going to go ahead and save that and then go over to simulation. Click on the test bench and then double click on simulate. Let me close my other iSIM here. I've got an error here. I think we need to include another library. Let's try that again. Okay, so right now you can see we have some values of the switches. They started at 0. This is only going to 100 nanoseconds, so we can type here in the console to run it for longer. I'm going to say 2000 nanoseconds. So if you look up here, you can notice that our switches are incrementing by 1 as expected, but the output LEDs are staying 0. And remember, we had decided that the output LEDs should be the reverse of the switches. So in this case where you see the yellow bar, our switches are 4 zeros, 0, 1, 1, 0, and we would expect the LED output to be opposite of that. But since that's not the case, we have got an error somewhere. So how are we going to use iSIM to help us find that error? Well, we need to start adding some more signals to look at. First, let's look at our program. And let me start this over again. So if you notice, we are going to be using the in instruction, the move instruction, the XOR, the out, and the branch. So the best thing to do is to step through each of these instructions and see if the values are moving through the CPU as expected as a result of each instruction. So we're going to start with the in instruction. The in instruction is going to get a value from the switch port and put that value into R10. So we need to look at those internal signals in iSIM. So what you can do here is on the left hand side you've got your test bench, your unit under test, this UUT, which is your CPU. We're going to go ahead and add the in port and the out port and the port ID. And we'll add the output enable signal as well. And we can add some banners in here. New divider. I'm going to call this IO for input output. I'm going to move the divider up here. Alright, we're going to get some signals from our register file. I'm going to get the input for the register file. And I'll go ahead and get the two outputs as well. We'll add another banner, a new divider, register file. Move that up. Okay, I'm going to go ahead and get rid of this clock period and the reset signal because we don't really care about those right now. Alright, and let's also, since we're also dealing with an XOR instruction which is using the ALU, we'll go ahead and get the inputs and outputs to the ALU. And I'll go ahead and add one more divider. And the most important thing that I think is important to add is your program counter, so you know what instruction you're on in the program. I'm going to put that up here. PC count is going to go, it doesn't like me. Let's try this again. Maybe down here. Alright, now I'm going to move it up. There we go. Alright, so now that we have this all nice and set up, you can go ahead and click on the relaunch button, and we can save this configuration, my config, so that way you don't need to always add the beautiful banners and signals every single time you want to open ISIM. You could just open the config file. Alright, so let's see what's going on here. Once again, we're only running this for 100 nanoseconds, so we're going to run it for longer. If you hit this zoom full button, we can get to the beginning. Now it's also helpful to change these values to hex. I'm going to change that to a hex value because looking at tons of ones and zeros is very tiring to the eyes. Alright, so let's look at our PC count. Now if you remember from our program, here I started the origin at hex 10, so that's going to be where our first instruction is. Everything before then is not going to matter very much because there's no instructions located anywhere before hex 10. So we're going to look at the program counter and find out where hex 10 is. Yeah, so here you see the program counter incrementing. If your program counter is not incrementing, you probably didn't initialize it. Alright, so the program counter is incrementing. Now, here we see it reached hex 10. And you can see each instruction takes, you see where the yellow bar is, it takes 2 clock cycles, 1 cycle, 2 cycle, because it has a fetch and an execute. So this first instruction at hex 10 is an in instruction. Now if you look at the switches where my yellow arrow is right now, the value of the switches is 3. And as you can see on the import, we do have the value of 3, so that's working correctly. On the in instruction, we want the input to the register file to also be 3, or the value from the import, and it is, so that's good. And we're not dealing with the ALU, so that doesn't matter. So far the in instruction is looking pretty good. Alright, what is our next instruction? Our next instruction is the move instruction. So we're going to be moving FF into R11. So let's see what happens. Here on the execute of instruction 11, which is the move, we need to move FF into R11. So the input to the register file should be the value FF. But look at what we have here. The DIN for the register file is 0. So that already is telling us that we have a problem on the second instruction. We were expecting the input to the register file to be FF, which was the value that we want to put into R11, but it's not. So we've already got a problem on the move instruction. Now, how are we going to determine what exactly is wrong with this move instruction? Well, if you recall, the register file input is based on a MUX selection. So it might be helpful to see what are the inputs going in and out of the MUX that's going into the register file. So we can look at that. People implement their MUXes in different ways. Here I have a register MUX. So I'm going to put in all of my MUX choices into this register file category. I'm going to put in A and B, and C and D, and the output. Okay, so as you can see, some of the signals showed up for us and some did not. I'm going to go ahead and change the radix of these to hex. I'm doing this by right-clicking . Alright, since we don't know what D and C are, I'm going to go ahead and relaunch this. Oops, relaunch. Yes, please. And we're going to run it for longer again. And let's go ahead and go back and find our instruction 1.1. Look at the PC counter. There's instruction 1.1, which is the move that we are on. Okay, so remember we found out that the input to the register file, which was this DIN, was 0 when we wanted it to be FF. So if you look at our input choices to the MUX, we do have an FF as one of the input choices to the MUX. but that is not what went into the input. So this mux out signal should match exactly with this D in signal. And so as you can see, it took the value of either A or C, because the value going into the D in is 0, and the C input was a 0, and the A input was a 0, but we wanted to get the B input, which was FF. So there's something wrong with our mux selection, and we need to figure out what that is. So now we can go back to our mux selector in the code, and that for me is in the CPU file. Alright, here is our register mux port map. And my first input is the import, my second input is the sum, my third input is from the stack, and my fourth input is all high impedance right now. And is that what I really want to have happen? Well, I need to check my actual mux file. So in my mux, my A is selected when I have option 0, 0, B is selected when I have 0, 1, C is selected when I have 1, 0, and D is selected when I have 1, 1. So the question is, did I put these things in the right order? Did I want the import when the select is 0, 0? Yes. Did I want the sum when the import was 0, 1? Well, this is where the problem lies. I actually wanted these two to be reversed. If I go back to my mux table or my control signal table to see what control signal is supposed to give me what selection. So I had these two reversed. So I'm going to save that, and all you have to do is change your code and save it without closing iSIM. You can then go back to iSIM and once again relaunch. Okay, I'm going to go back to PC count 1, 1. I landed right on it. And now look at that. In our register file for our execute cycle of 1, 1, we see that the mux out is now FF, which was the C selection, and the input now to the register file is FF as well. So now things are looking a lot better. We got what we wanted to have happen as a result of this move. So we can now move on once again to the next instruction. We have an XOR and then an out. So let's move to the XOR, which is the 1, 2. On the XOR instruction, we care what's going into the ALU. So the inputs going into the ALU are 0, 5 and FF. Now, did we want 0, 5? Well, at this point, yes, the switches are at 5, so that was the value that was put into the first register. FF was the value that was put into R11, And when you exclusive OR those together, 05 exclusive ORed with FF, does that give you FA? I have to quickly write this out to double check in binary. Yes, it does give you FA, so that's giving us the right value. So our exclusive OR is working. Now if we go to the last instruction at address 13, notice now that we're doing an out, and we want the value that we got as a result of the exclusive OR, which was FA, to be on the out port. And look at that, it is. And the output enable signal has to also be high during that cycle so that it can be output to the board. So because we have the correct value on the out port and the correct output control signal, everything is looking great. The following instruction at address 14 should be a branch, and basically what you're looking for on a branch is the next program counter the address of where you want to branch to. And because we want to branch back to the beginning, which was at address 10, if you look at the next program counter, it is 10, so everything is looking really good. So now we can just double check if everything's working right up top. We have to find where all of our outputs are. So here, our output, we had the input value of 5, and after the output occurs, which is at this clock edge, you can see on the LEDs that we have the reversed value of the switches. And this is going to change again once we hit the output again. So here is our next output enable signal. At that clock edge, we should get the opposite value on the LEDs. So the switches at this point were 4 zeros, 0, 1, 1, 0, as you can see above here, and the output is the exact reverse. So everything is looking like it's working. So once you get it to this state, then you can go ahead and try it on your board. So I hope that gave you a good overview of how to use iSIM. It's a very powerful tool, and feel free to add and subtract signals as you need as you're finding bugs through your code.